Here we go. So we're up to subtopic 3.10, so 3.10, which is the last one of topic 3. Now this one is about proteins. Like the last couple, it's going to be involving a few of the different groups that we have covered before. So let's start with. There we are. Just got to get myself my little laser pointer. Good. So we have looked at polymers. Proteins are polymers. They're specifically polymers of something called amino acids. Now, amino acids, from the name, you've got an amino part of that name. So that's going to be related to our amines, so our nitrogen-containing group, so NH2. And our acids are going to be related to what we saw in 3.5, which is the carboxylic acids. So our amino acids have both of these groups within them. Now, you can see that in this structure here, so this generic structure, we have an amino group on one side, which is an NH2. It's connected to a carbon in the center, and attached to that carbon in the chain is a carboxylic acid. So another carbon attached, double bonded to an oxygen, attached to an OH. Now, the amino acids are different by way of their side chain. So on that middle carbon is extending a side chain, and what that side chain is will determine what the behavior of that that amino acid is, and there's other effects that we'll be talking about a bit later. Either way, every amino acid will have a name, and that name will correspond to a different side chain. Now, as I said, the R group can vary. The amino acid named alanine, for example, just has a CH3 attached to that carbon. Now, where are we? So I'm going to add in some details here. Now, the behavior, they're all the same in the amino, or actually most of them are the same in their amino and carboxylic acid sections. The differences are the side chains, and those side chains have different, allow the amino acids to have different intermolecular interactions with other molecules. So if we have alanine, that is a CH3. It is a non-polar side chain, which makes our overall amino acid considered non-polar. Now, on the other hand, serine, which is our next one with the OH group, it has a hydroxyl group in that side chain, so that makes it a polar amino acid. So not only is it polar, it can hydrogen bond with other molecules because of that OH group. Now, as we go down, so the amino acid, so we're not looking at the proteins yet, we're looking at the pieces that make them up, the amino acids. Because of the fact that it has an amino group on the side, it can act as a base. In other words, it can accept a H+ from another molecule. Now, also, it has a carboxylic acid group on it, which can act as an acid. So that means that this bit here, it can donate a H+. So it can become our carboxylate ion group, which has lost its H+. Now, the interesting thing about these amino acids is that when you have a neutral pH, they're just chilling out. They're actually not, they're not neutral on both ends. They are going to be, most of the time, they're going to be neutral overall, but that's only because each of the side chains has ionized. So it's called self-ionization, where the H+ from the carboxylic acid group attaches to our amino group. Now, I've shown you a little bit of a mechanism down here. Pretty much you can see the electrons from the nitrogen, so the lone pair on the nitrogen, they go over to this the hydrogen. The electrons from that OH bond go onto the oxygen. That makes this oxygen negative, and you form a bond between the nitrogen and the hydrogen. Now, obviously, nitrogen here has 4 things attached to it, which means it can't, it's not going to be neutral. It ends up being positively charged because it's essentially had that lone pair of electrons that it was all of its own. It's now sharing it with another atom. So it's essentially losing that share of an electron, making it a positive charge. Now, if our amino acid was in an acidic environment where there's lots of H+, you're going to end up with a hydrogen attached back onto that acid, and you can end up with a hydrogen attached to that amino group. So essentially, when it's acidic and there's lots of H pluses, you put H hydrogens onto everywhere it can be. So one spot is here, one spot is here, they're both there. Conversely, if it's a basic environment, that means there's not, there's lots of OH, for example, that is going to take away every H plus from the locations they could be. So the OH here has lots of H plus, and our NH2, it does not have that additional H plus on it, as it was over here in the neutral and the acidic. So if there's an extra H plus, if there's a H plus there that can come off, it will take it off when it's in a basic environment. So that the OH and the additional hydrogen that was on there when it was neutral. Okay. Now, I've said it here, I've already mentioned it. It's important to remember that when you are in a neutral environment, you are going to have your amino acid self-ionized, so ionized on both ends, and we call that a Zwitter ion. So the neutral, we have our Zwitter ionic molecule. Now, we've looked at amino acids. There's a whole bunch of them. You'll see lots of different versions of them throughout all the different questions and in the exam and stuff. As long as you can recognize looking at the side chain, recognize the type of intermolecular forces that are likely to be happening because that group is there, then you should be okay. Now, when we go down to this next bit, as I mentioned earlier, we know that those amino acids can form polymers, and we're going to look a little bit more closely into how those form. Now, an amino acid has an amine group on one end and a carboxylic acid group on the other, which means you can take carboxylic acid and you can that carboxylic acid side chain of the chain, and you can form a condensation reaction between the carboxylic acid group and the amino group to form what's called a peptide bond, which is a type of amide. So from 3.8, we had our amides. This is what we form. This particular version of it is called a peptide bond because you're joining amino acids together. Now, if we join one amino acid with a particular R group to another one with a different R group, you're going to end up with what's called a dipeptide, which is it's the beginnings of a protein with two amino acids attached to each other. Now, this bond here, where we have our carbon R group and our NH, that is called a peptide bond, and you always are going to be yielding a water molecule. So we lose the OH from the carboxylic acid, and we lose one of the hydrogens from our amino group, and that comes off as water. Now, I have another point that I'm going to make in a moment, but before I do that, I've got arrows going back and forth here, and that is because you are going to be required at some point to be able to join two amino acids, join amino acids together, yielding water. You're also going to need to hydrolyze, which means add water to a dipeptide or a tripeptide and break those bonds and draw the amino acids that did make up this di or tripeptide. So you're going to have to do this in both directions. You're going to have to combine them together as well as break them apart. Now, here I've drawn a dipeptide, and it's got our side chain, R side chain, our R prime side chain. We've got the R side chain is attached via the carboxylic acid. The R prime is attached via its amino group. We could have swapped the orders of them. So we could have had this as being the R prime and this one being the R. That, if that was the case, just because it appears symmetrical at first glance, does not mean it is. They are different molecules when you attach them in a different order. So if you have two amino acids, you can actually make two different dipeptides. One where it's R prime, and the other one where it's R prime R. So an example from earlier, using serine and alanine, we can have ser-ala. So that's a way, there's a 3-letter code that goes with each of these amino acids. So if you have SER, that's serine, ALA is alanine. If you make SER, ALA, join together like that, it is joining them together in this specific way, where our serine is attached via its the carboxylic acid side to our alanine through its amino side. If you were to swap the orders, you'd make ALA SER, ALA serine, and that you'll see how the alanine is attached via its carboxylic acid side to the amino side of the serine. So it's opposite. These are different. They have different functions, they have different purposes. The order of them matters. Okay, so now we've covered that. When we join multiple of them together, as I mentioned earlier, you're going to end up with a long chain. Now, these long chains are going to interact with each other and other molecules through intermolecular interactions. Now, these intermolecular interactions are pretty much completely dependent on the type of intermolecular forces that those side chains can bring to the table. And I've got some categories here and an example of each of them. Now, there's electrically charged side chains. So if we look here, we have our NH3. It's a positive or a basic side chain, and it's going to have a charge on it most of the time. So you're going to end up with some, ion, in this case, the one we see here is positive / basic. You can have acidic ones as well that are going to be negatively charged. Regardless, these are going to introduce ionic bonds or ion dipole bonds with other amino acids in different places. Now you can have polar, so an alcohol group on the side chain. Now those, while they're not charged, they do add the ability for this molecule to hydrogen bond. So that's a pretty strong intermolecular force as well. Again, there are other types, not just the OH, but you can have other types as well. Now, there are hydrophobic ones. So like our alanine earlier with a polar, the non-polar side chain, you can have a whole bunch of other ones that are non-polar as well, because they're just made of hydrogens and carbons. A lot of them are going to be mostly alkanes. There's also aromatic ones, which are made of benzene parts, so bits like this. Either way, all of those, they are only really going to be introducing dispersion forces. Now, there are some special cases. So an example would be, I can't remember the name of this one, but the side chain actually attaches around to the amino group. So obviously, its interactions with other molecules are going to be a bit different to the other ones. There are some other special cases as well. Not really important that you have to deal with them. You're probably mostly going to have to deal with the other ones that have a more clear intermolecular interaction that they bring. As I mentioned here, you've got ionic, ion dipole. You've got polar with dipole and hydrogen bonding. You've got hydrophobic with dispersion. Special cases are special. Okay, now when you make a protein, you're going to be attaching one amino acid to another, to another, to another. That's what we call our primary structure. What amino acid is it? What amino acid or which amino acid is attached to which amino acid? So that order. Now, secondary interactions is when you get these amino acids interacting with other amino acids that are somewhere else in that chain. So not the ones immediately next to them, but somewhere further along, because these long molecules can bend. If they bend back on each other, there's going to be some secondary interactions happening. So those ionic, ion dipole, hydrogen bonding, etc. Now, those secondary interactions, what they do is they allow the protein to fold into tertiary as well as quaternary structures. I'll talk a little bit more about them soon. Yep, just a bit down a bit lower. But the important point is those interactions are really important for those structures of these proteins, and the structure is the function of these proteins is almost completely dependent on their structure. So if the structure is messed up, because the order of the amino acids is wrong, or the chemical environment. So, the pH has been messed around, so the intermolecular forces are stuffed around, then it can destroy the structure. And if the structure is gone, the function of that protein is also gone. Now, if we look at the pH, the effective pH, some side chains can have their behavior changed. An example would be this side chain here, which is a carboxylic acid in a basic environment. It has our O minus. In a acidic environment, so if the acidity goes up, you end up gaining that OH back. In this case, you've lost our charge. That means any ionic or ion dipole interactions that were there are now no longer there, which reduces the strength of those intermolecular forces, which could potentially break the structure. So, another thing that can happen is, if you heat up proteins, they can do something called denaturing, which is, again, disrupting their structure. If you put energy in, it's almost like melting the structure. You've got your intermolecular forces, even though they're within the same molecule, they're on different parts of the molecule, they're close together. If you heat it up, you can break those structures, and that will break your molecule, essentially sort of melt it. Not exactly melting it, but sort of. Now, just a quick summary. So this is the last bit. Summary of all the structures of that protein. So we have our primary one, which, like I mentioned before, we have our amino acid sequence. So these are covalently bonded through peptide bonds. If I'm just putting A's and B's and C's and D's here, but if you have A attached to B, attached to C, attached to A, D, E, whatever order that is important. But whatever that order that is the primary structure of our proteins. Now, the secondary structure are the individual, the intermolecular interactions that happen between distant parts of the amino acid chain. So if you have a chain folding over, you can have some intermolecular interactions, that happen between them. Those interactions can form certain shapes. So two of the most common shapes are what's called alpha helixes. So alpha helix is like a helix shape, like a spiral. Another shape that is commonly formed is what's called a beta pleated sheet. I didn't actually call it pleated sheet here, but that's what they normally call it, pleated. So because it's got a bit of an angle to it. Either way, if you have, you'll end up having like a sheet of interactions. So sort of like that. Now, these little sections that have these bits will all obviously join together, and those will give us our tertiary structure. So our tertiary structure is joining up our helices and our sheets, as well as just our regular bits, together into an overall three-dimensional structure. So I've given an example here. We have an alpha helix here that joins through into a sheet, which joins into another helix, and you can have a whole bunch of this stuff going on. If you were to Google the structure of any particular protein, you'll see something like this happening. Now, there is one extra level, and we'll finish with this, and that is quaternary. So the fourth level structure. If you have one piece like this from one amino acid sequence, you can actually make composite proteins where you have one protein molecule here with its particular structure, and you have another one with a separate molecule with a separate structure, and they can actually join together through intermolecular forces, intermolecular interactions. They can join together to make a quaternary structure. So if you have an overall protein that has multiple separately bonded pieces, that gives us our quaternary structure. So that happens a decent amount of time. So I think that's pretty much it for proteins. And I hope this information has helped.